And then finally, we have some thoughts outside of Data-on-MDT that we're also investigating early on at this point to improve small file I/O performance. So first, a few concerns. So small files are small, right? So the concerns, some of the areas of improvement or concerns is that a small file residing on a single OST doesn't have parallel access to that data. Also, the data being small means that we can't do things like read ahead. And we found in our investigation that RPC and RPC pressure was a major or a significant hurdle or roadblock preventing us from getting further performance out of small file I/O. So the third one in the middle bullet up there as well is one of the concerns is the overall negative effect on net performance that we'd have with one data stream for both large streaming I/O and small file, intermittent small file random I/O occurring at the same time. Our testing showed that that leads to more seeking and slowdown and an increase in latency as opposed to having two separate data streams. So the good news is we have something that can help, and that's Data-on-MDT. So Data-on-MDT aims to improve small file I/O performance. It's not the all singing and dancing solution that will solve all small file I/O concerns, but it does aim to address the concerns that we're talking about on the left-hand side here. And it does that by storing the data directly on the MDT. And it has the capability for, as that file continues to grow beyond a specified limit on the MDT, it'll continue to grow on the OSTs. And phase one of this feature was introduced in Lustre 2.11 that was recently GA. So as far as the foundation or the basis of the feature, again, it aims to improve on those targeted areas of small file I/O performance. And it does so by trying to avoiding the RPCs between the MDT and the OST that would otherwise exist if we were writing to the OSTs. And that helps us by reducing RPC pressure on the OSTs, although it does increase RPC pressure on the MDT, which we'll talk about later on in the presentation. And it gives us that separate large and small file I/O data streams, which will reduce the I/O overhead on OSTs and also avoid blocking those small I/Os behind large streaming I/O workloads. Also, with this solution of having the data resident on the MDT, there's some other benefits that we'll talk about that we can take advantage of with the data residing there beyond just reducing RPCs, but we'll have some other improvements that we're going to target for phase two since the data is accessible with the metadata operations. And by definition, or in many deployments rather, MDT servers are often faster, and so it naturally contributes to an increased performance by putting data directly on the MDT. And the underlying storage type, as we'll talk about, can be a large factor in what that performance gain may or may not look like. So as far as the implementation overview, what Data-on-MDT is, a DOM file is simply a PFL file. And it's a PFL file where the first component resides on the MDT. And as specified, it will continue to grow on the OST when that data limit is reached. And there's two types of limits, and we'll get into those as well. Now to do this, a new layout for Data-on-MDT files was introduced. That's the -L MDT. Flagged to LFS set stripe. And to do this, we had to modify both client and server code. So the client code was modified to be able to send I/O requests to an MDT, and then obviously the server side code was modified to be able to serve those I/O requests with new I/O service threads and methods. And at this point, basically the MDT and the OST become nearly the same for I/O request handling. So where can Data-on-MDT help? So obviously it would help with small file data residing on the MDT, especially for read and stat operations. The read performance, as you'll see, is quite good. We also have further improvements planned, and just, it's a little teaser here basically, but we'll talk about a few of them. One of those is called read on open, but that data read stat operations is one area where Data-on-MDT will be very beneficial. The second is it reduces the amount of small random I/O that's occurring on the OSTs. So again, having separate data streams should improve latency for both large file I/O streaming and small file I/O, especially if the OSTs are using hard disk drives with RAID 5 or 6 redundancy. And not much is for free these days, but if you have an MDS MDT already with better storage and is faster, considering maybe an NVMe versus hard disk drives on your OSTs, this benefit basically comes for free without having to do massive upgrades of OSTs just to increase small file I/O performance. So this, as I said, it's not an all singing and dancing solution, so there are some things to be aware of, especially here in phase 1 of the feature. Basically, a Data-on-MDT file write has the same amount of operations as an OST write, especially if the underlying hardware is the same on the MDT as the OSTs. You may not see a large performance gain for writes themselves. Also consider the case where, of parallel write efficiency that's offered by writing to OSTs. So for example, if we have n small files and we have n number of OSTs, we could, in theory, write all those small files at once in parallel. And with Data-on-MDT, especially if you have a single MDT, obviously you can't achieve that same parallel write efficiency by definition that you could with writing to OSTs. Now, DNE may be able to help with this, but the reality is you're going to have more OSTs than you will MDTs, so again, by definition, you won't have that same level of parallel write efficiency as you would with writing to OSTs. As far as file creates and metadata operations, so metadata operations will be the same performance for a Data-on-MDT file as an OST file. And I know many people will be thinking about the file create rate. At this point, performance is flat at best for file creates because Data-on-MDT file has to do some extra work to create and write a special layout that normally we wouldn't have to do. And this is an area that we're targeting for improvement in phase 2, focusing on reducing the expense of that operation. So just a few things to be aware of as we move forward with Data-on-MDT. As far as the limits that we had mentioned about, there's 2 limits. There's per file limit, which is the amount of file data to store on the MDT for that file. It can be set directly with LFS set stripe, as we have seen, and it also can be inherited from the parent directory. There's also a per MDT parameter, and that's the maximum data size that server is going to allow for a Data-on-MDT component. And that can be set and saved in the config. Now, as we're talking about it, I'm anticipating one question already is which one wins. And the way it works in phase 1 is the server limit will win provided that the file doesn't already exist. So if you have for example, you have a DOM component and then you've reduced the server limit, obviously, that file already exists. You could touch that file, but if you tried to create a new file that's above that new limit, then you would have failure in creating that file. So a few examples. The first example is creating a new file with a 1 megabyte DOM component. You'll see the -L MDT flag again, which is new. And you'll see the size is being specified for the first meg to be placed on the MDT, and then would follow the rest of your striping options. The second example shows set stripe being set for an entire directory. Okay, so it has the first 64K being placed on the MDT, followed by the rest of the striping options. And to get information about DOM files, we use LFS get stripe. You see there's now a -L MDT option, as well as LFS find with -L MDT. And I believe we have an example coming on the next slide. So if we go back for a second, the next slide will show the example of get stripe on this create right here, where it's creating it for a directory. And you'll see now the stripe size of 64K and the pattern set to MDT as opposed to RAID 0 for the other components. that are residing on the OST. Also, the server-side limit, a quick example. So that's done with a DOM underscore stripe size parameter that now exists. And that, again, controls the maximum size that will be allowed for a DOM component by that specific server. And setting it to 0, which is the last example, will disable DOM files for that server. So again, just a few examples to step through. Set param being called with DOM underscore stripe size set to 64K. The second example using set param -p with DOM stripe size being set to 2 meg, and using get param to be able to retrieve the current setting of DOM underscore stripe size. And the last example is showing saving it in the config with conf param. And again, what's being set here is stripe size being set to 0, which would disable Data-on-MDT being used by that server. So let's get into a little bit of performance testing. And I'll say it several times, but and it's shown on the next slide, but our test bed here was all NVMe storage. So there's no hard disk drives used. And we had one MDS with one MDT. We had 8 OSSs with a total of 32 STs and 16 clients in our configuration. So the servers each were Intel Xeon 2697 Haswell CPUs. The MDT had a P3700 NVMe device. The OSTs had P3600 NVMe devices. The clients were Intel Xeon Scalable 6148 CPUs. And you can see the optimizations that were on the server at the time of this testing. Now, this testing is done with the 211GA version of Data-on-MDT. You'll see that we do have some optimizations in flight for phase 2, but none of that work is part of these test results. So in terms of our testing, we focused on IOR and FIO for detailed read-write, and then Compilebench and dbench for simulating user activity that targets metadata and small file operations. We had 3 different striping cases that you'll see in the results. You'll see that we compare an OST file with a single stripe, an OST file with striping set to -1, which is 8 stripes in our scenario, and then a Data-on-MDT file. So the first graph here shows IOR write for small files. So it's less than the DOM limit that's set for that server. And what we see here is, looks like it's big enough to read, but the first bar is Data-on-MDT, second is the stripe -1, and third is a single stripe file. And since all storage here again was NVMe, write performance is fairly good for small files across the board here. We see Data-on-MDT is showing improved performance as the client count increases. Also, we see that the -1 striping really stands out as off from the other two, mainly because the more stripes, the more RPCs we have, and as we said, RPCs is part of the roadblock that we're trying to avoid and by improving performance here. So Data-on-MDT showing write performance, scaling pretty well as the client count increases, looks pretty good. So in terms of read performance, again, for the same type of file, it's a small file less than the DOM limit. And what we see here is strong performance from Data-on-MDT compared to the -1 striping and single stripe, which are nearly identical. It's obviously, with the 8K reads, there's more RPCs, so DOM really has a nice curve, and there's a bigger delta than, say, the 64K reads. But DOM is significantly better across the board, and we achieved the expected result here with read performance. We also wanted to do our due diligence and check files that are over the DOM limit to see, is there any performance degradation by using Data-on-MDT for larger files? So in this, we have the DOM component residing on the MDT, and now the file has grown outside of that limit, so it has a second component that's sitting on OST. And what we see for writes, again, there's no performance degradation, and if we see the oddity in the graph is the single stripe performance is lower than the DOM or the stripe -1, and that's because DOM itself is at least 2 stripes, right? So the first component's on the MDT. So really we're comparing 1 versus 2 versus 8 in this case. And we also show read performance. There's no degradation either. Those results are pretty much flat across the board. Now we've included the Compilebench results here, and the graph changed a bit. So what we're comparing here now is local directory striping, single stripe, -1 striping, and then the DOM file. And we include it because out of the box in phase 1, not all cases show an immediate improvement with Data-on-MDT. And talking with Mike about this, what's likely going on here is that expense that we're paying in the file it creates right now that we talked about earlier in the presentation. Now, we've also done some dbench testing that we didn't have we weren't able to run dbench on this test cluster, so we didn't want to include the graph as it wouldn't have been a fair comparison. But we've seen strong results at a dbench, so this is an area where we really have to dig in and understand what's going on and focus on that optimization for phase 2. So speaking of phase 2, what's coming? So there's still a significant amount of work to do. Phase 1 really focused on the framework and stability of that framework. In phase 2, we're going to cover optimizing Data-on-MDT with a DNE configuration. We want to handle migration, we have a few optimizations that we already have in flight, and I'll step through each of these. So first, DNE. So notice that it says DNE optimization and not integration. So it is integrated. DOM will work with DNE out of the box in phase 1. Now we did run it on this test bed, and we saw some interesting results. And the testing what we had with all NVMe wasn't really a good test to be able to rely on for DOM plus DNE scaling because the servers weren't under load. They were all using NVMe storage, and it was likely that one MDT was able to handle all the incoming requests. So adding more MDTs, obviously, in that case, didn't really give us a valid test. We have seen good potential for scaling when the servers are under high load with more localized testing. So fleshing that out in phase 2 is a primary goal. And you can see the LU ticket here if you choose to follow along to this work. With migration, we want to enable LFS Migrate to work with DOM files, and there's 3 cases. So the first case is migrating a file to the MDT that's currently on OST. So you have small file data out there living on OSTs. Obviously, you need a way to bring that in and store it on the MDT. The second is migrating 2 OSTs from the MDT. So for example, you have small file data sitting on your MDT. It's grown in size. It now has the rest of its file data on OSTs. And for whatever reason, you need to move that first DOM component to the OST as well. For example, if you need to reclaim space on the MDT, you may choose to migrate some of that data with the rest of the file components. And then the third is migrating between MDTs in DNE config to be able to do things like load balancing or space balancing. And again, when these slides are posted, you can easily click on the link there, and it will take you to the ticket that's tracking this work. Now, in terms of performance improvements that we're already thinking about, the first, and they all take advantage of the fact that the data is resident there with the metadata as well. And the first one is what we call read on open. And read on open basically does a read prefetch on file opening, so you get the data on file open. And this is a mature patch already in flight, and if you go to LU10181, you'll see that patch there, and those that are up for it may test with that patch. It shows increased performance for us in our early testing of the patch. But that patch is fairly mature and very, very far along. I'll skip down to the third bullet. So along those same lines, we have some ideas around reading data as well on stat and readdir. So readdir, for example, will return all the file data for a given directory when performing readdir. Now, I have had some conversation with people, and we know that there is some danger around that, around doing that. So this is just very early on in the process. There's not patches in flight for this. So we'll be carefully looking into that work. And then the third one, which is the middle bullet, the glimpse ahead. So, excuse me. Glimpse ahead basically allows the MDT to return size from the client on stat, which saves RPCs as well. So this work is LU10181 as well, and there is a patch in flight for this. It's not quite as mature as Read on Open, but it is available, and you can certainly try that and provide input to it as well. So what are some recommendations, basically, with Data-MDT at this point? So you want to make sure to review the MDT role more carefully with Data-MDT. And again, this link here, when you have the presentation, will take you to Data-MDT documentation. And you want to review that more carefully. Obviously, you need more space on the MDT, and the MDT will experience higher RPC pressure from writes going to and from the MDT and coexisting with the metadata operations as well. If you have a SSD-based Data-MDT, it's perfect for DOM, especially if you're using OSTs with hard disk drives or RAID 5.6 redundancy. You'll see a nice performance benefit right out of the box. And in phase 2, you really want to consider DNE setup, as you may have further benefits once DNE is optimized with Data-MDT to be able to do things like select certain MDTs specifically for DOM if they have better capacity or more storage. So you can kind of split where the DOM activity is happening across MDTs in the DNE configuration. And as I said up front in the beginning, there's opportunity to focus on some areas outside of Data-on-MDT. And we have one of our engineers currently looking at basically the RPC process for file creates. So the create and open RPC, followed by the LDLM and Q synchronous RPC, followed by the OST write RPCs, and finally followed by the MDS close synchronous RPC. So a few ideas. One is close in background, which basically seeks to make the MDS close synchronous RPC asynchronous, which will save us one fewer synchronous RPC. We also have an idea on saving on the NQ RPC if the open and create RPC would return an exclusive lock up front. So that'll save RPCs as well. There is an idea around multi-file read-write in a single RPC, which should help with the bottleneck around the write RPCs. We have an idea around the initial the client initial create and open handling metadata. So basically that'll really help with create burst for small files. And Andreas talked about this yesterday in his talk, so I won't go into it much here, but there is the idea around a client metadata write back cache as well, where we could possibly create files in RAM and write them back later, which would save on RPC round trips for creates as well. Oh, and in the middle, the improved block grants. So basically, Alex, one of our engineers, has been looking into this, and he has seen in testing that tiny IOs consume significant grants, and it turns asynchronous IO into synchronous IO in some use cases. So we have some investigation work going on into that as well. So while you read all the important things about this data in legal terms, in summary, Data-on-MDT phase 1 has shown quite good numbers. We're quite happy with it. As we talked about yesterday, there's two methods to releasing features, right? So we could, the perfect feature is still under development, and it always will be. So we use the phased approach here. Phase 2 is going to offer further performance gains. You're welcome to try out those patches already in flight. Certainly, we are welcome to hear your experience with it and your input into those patches as well. And then we do have some work that we're not just focusing on Data-MDT, but we're focusing on the larger problem as well with some of those very early investigations we've shown on the previous slide. So that's all we have. I think I used up most of my time, but I'd be happy to take questions. I'll do my best. Mike Persson is the one behind all the work, and if we have detailed technical questions, I may need to lean on my Intel colleagues to help me out.
So question over here. Mixing metadata and data on metadata, and potentially even another use case where you're converging, your MDS and your OSS in a common backend. So in InfiniBand, we see a lot of, congestion getting to these various resources, and we may want to have, QoS or traffic service level class for true metadata versus data on metadata. So have you looked at how that might affect the RDMA transport in terms of allocating, a service level to true metadata operations so that they could overtake those congestion that you may see now that we're pushing so much data to the metadata system?
Well, that's a very good question. I'm not aware of that too much of any investigation into that. If anybody else is as well, I don't think so, that we haven't really looked at that yet, but that's a very good point and something we probably should investigate.
So I noticed you had an example of 64K as the size on MDT, which is less than a typical 1 meg RPC. Let's say we're poor and we can't afford a whole lot of SSDs in our metadata target. What's the minimum useful size of an extent on the MDT for data?
Andreas, would you have any idea on that one?
64K is the smallest size you can specify. I mean, just because the Lustre stripe size is the minimum is 64K because some clients have 64K pages and you're not able to split a single page write across, 2 different OSTs, right? And so that's why today the regular striping minimum is 64K, and that's also carried over to the MDS. I mean, obviously, if you create smaller files, then well, yeah. No, if you create smaller files, it'll use less space, but the minimum you can enforce is 64.
Could you say a few more words about the potential DNE optimizations? I didn't quite understand what you had in store for that.
So what we saw in testing the DNE config, which we did test in that test cluster, but what we saw was the servers weren't under load, and one MDT was likely serving all of the metadata requests, and we didn't really see scaling that we would have liked to see. So it really wasn't a fair test for Data-on-MDT with DNE in this test bed, since everything was NVMe and the servers weren't under load. What we've seen in other testing where servers are under high load on a different infrastructure, so more local testing on a smaller scale, we do see good scaling with DNE. So what Mike is going to do is he's looking at what was the difference between the two, understand our results a little more. These results are very fresh, and then look at what optimizations do we have to make to be able to handle multiple cases with DNE, including cases maybe where all the underlying storage is the same. Does that answer the question? Do you have a follow-up?
So you just want to explore the space a little bit and then see what low-hanging fruit might be out there or whatever. Because I looked at this LU 10895 and there aren't any details there yet. So it's just to explore the space and then see what we can find, kind of
Absolutely.
thing. Okay.
It's
Right.
very
Great.
fresh results, and we saw that. We were quite looking well. We saw in our testing, on Mike's testing, with under high load, he saw very good scaling. But then in this particular test bed, may not have been very good to exercise the benefit of DNE plus Data-on-MDT. So we just have to understand it better.
I could see in like the 211, maybe phase 2 with the DNE being useful, because I can imagine, a user just saying, oh, I can get my stuff really, really fast if I have all of my data set up so it's under that size and everything is on MDT, and then you could be filling your MDT up. So I like the fact that in phase 2, you can say that it will be somewhere else. So if you can add hardware, you can say that this is, all of our metadata stuff, but for the actual data, you can actually put it somewhere else so that if someone tries to kind of, you know, work the system, as it were, it doesn't necessarily stop everyone else. And I don't know if there's a better mechanism for, you know, preventing a wily, crafty user from just filling up your MDT if you have this data on MDT, but, you know, I'd be all ears for that because someone will try it.
Sure, that's a, that's a very good point.
Thank you. We probably need to give Patrick enough time to give everything, but let's give him another round of applause.
Thank you.